Radek. So I'm happy to be here because I was a bit sick before coming here, so my participation was in doubt. Anyway, okay, my talk will be about the perspectives of having a public code about multiple lensing with contour integration. So I will speak about the current challenges and the current perspectives. Okay, so all of you know that in order to calculate the microlensing amplification, we have two branches for possible approaches. One is the inverse ray shooting, and the other one is contour integration. And in my case, I followed the second approach with the contour integration. So I developed this VB binary lensing that is now very quite widely used. It's a public code. It's on GitHub. It's written in C++, but is also importable in Python, thanks to my collaborators, Etienne Bachelet, Fran Bartolich, and Marco Sundertmark, who did this wrapping in Python. It is very, very easy to use. And so now VB binary lensing is used by all main platforms for modeling. So this is the list of platforms using VB binary lensing at the current time. Just a few words about how it works. So the basics is contour integration. That means that in practice, we sample the boundary of the source with some points, and we invert the lens equation, and we get the corresponding points on the boundary of the images. Once we have the points on the boundary of the images, we can use the Green's theorem in order to integrate and get the area of the image. So this is the basic idea behind the contour integration. In my case, I also have implemented a lot of speed ups and fancy things. For example, the parabolic correction, so that the accuracy of the calculation is greatly increased. There is error control on each arc in order to assess the accuracy, the current accuracy, and there is optimal sampling, so we don't overshoot with too many points, because after all, we have reached the needed accuracy. The basic calculation is for a uniform source, but you can also obtain limb darkening just by repeating the calculation on concentric annually. In the current package, you also have the possibility to draw light curves with parallax, satellites, circular orbital motion. And in the latest version, there are also further optimizations. So, for example, the decision 3. So the contour integration, the full calculation is triggered only when it's really needed, when the quadruple correction to the point length, to the point source approximation is sufficiently high. And also, I use pre-calculated tables for the extended source point length calculation. Okay, so this is what we did so far. Now let's move to the n-body calculation. So let's go back to the lens equation. The lens equation with the n lenses looks like that. And this is in the complex notation, of course. So the over bar is just a complex conjugation. So this is the original lens equation. The traditional approach is to convert it to a polynomial using the conjugate equation. So you can get rid of the z bar and rephrase everything in terms of z. And you get this very long polynomial with a degree which goes as n squared plus 1. But once you see some of the theorems that appeared in the literature, many of them due to Ree and then Cavinson and Neumann, so you can see that actually the number of images, the minimum number is linear in n, and the maximum number of images is also linear in n. So actually this square n says that we are actually overshooting. We are complicating the problem too much, probably, because we still want to solve a linear problem with the quadratic method. So how do we solve this very large polynomial? Typically, we use traditional methods such as Newton's method, and its a second order version, which is Laguerre method. These two methods can be combined in an optimized method, which was due to Ian Scoran and Andy Gould in 2012. So it switches between the two methods when you are close enough to the root. And this is the algorithm that is finally embedded in the VB binary lensing 2.0. Once you find the root in a polynomial, you also have the possibility to divide the polynomial by the root you already found, and so you can repeat the algorithm to find the next root. So you are guaranteed that you will not find the same root as before. But every time you do this, of course, you introduce numerical noise. And so this is the main limitation coming from this polynomial approach. In practice, we know that we have many images that come from cancellation of large terms. In particular, all negative parity images come from cancellation of large terms. And so the numerical accuracy is completely lost when you want to go from binary lenses to triple lenses or quadruple lenses or whatever. So for example, this is a planetary image, so a very small image close to a planet for the case n equals 3. But when you go to n equals 4, then you get this, solving the polynomial. So practically, it's completely useless. So how do we face this thing? In practice, we learn from this that we cannot trust the polynomial too much. In the end, the polynomial is a fruit of many operations, many manipulations, and it loses the numerical accuracy too much. So this is just with the double precision. Of course, one possibility is to go to quadruple precision, but of course, this means that your code will be much slower because your numbers will have a lot of bits in less of the classical number of 8 bytes. Okay, so my work in the last two months has been to find an alternative to this polynomial approach. So I went back to the original lens equation. So this is the original lens equation. I don't want to build this polynomial. Well, how do I solve this lens equation? Well, we can just repeat Newton's algorithm. So the philosophy behind Newton's algorithm is that if we are close enough to the root, then if this is the root, we can say that our current position is actually close to the root plus some small quantity. And then we can expand the lens equation close to the root. So if we define our lens equation functions, just taking everything on one side of this equation, we can make an expansion. So if we evaluate the lens equation function at the root, of course, we should get 0. But we can rephrase this thing using a first-order expansion. So this thing is equal to the current value of the lens equation function plus some small quantities in epsilon. So this is just a first-order expansion in epsilon. Now we can couple this equation with the conjugate equation and solve for epsilon. And so in the end, you get your increment. So this is the key to solve the problem. In practice, if you start from an arbitrary position z, this equation tells you in which direction you have to move in order to go to the correct image. And so this j here is just a Jacobian, so nothing really special. Okay, so once we have this this thing, so we can iterate and use this Newton-like approach in order to find images without the polynomial. You can also go to second order if you like, so you can make a second order expansion and get also the second order correction if you want to be faster in your calculation. And there is also the possibility to avoid the roots already found by dividing the lens equation by a pole on the image. So if we instead of using the lens equation function, we divide it by a pole on the image, we can repeat the same steps and obtain a new formulation for epsilon, which includes this function with the pole. And so in this way, we can avoid roots already found. Okay, so let's check whether this is more efficient than a polynomial, because we have the traditional approach and we can say how many operations we need to find the root. For a single step with Newton's method, in the polynomial approach, you can find that you need 2g plus 1 multiplications, where g is the degree of the polynomial. And I remind you that the g scales as n squared plus 1, so it's quadratic in n. While for the lens equation approach, this just requires 3n plus 1 operations. So in general, this one will be much faster than the polynomial with a smaller number of operation. Say when you, for the very last few roots in the polynomial, once you have divided it's for all roots found, then it's faster for the last few roots. But for those roots, of course, the accuracy is very low. So this Newton's method of the lens equation is faster and accurate. Let's check it. So this was the former situation with the planetary image for n equal 3 and for n equal 4. Let's check what happens with this new approach, and then you get the correct image without any problems, without any numerical problems. You can go even higher. So this is for n equal 10 with 10 lenses. Of course, it's just displaced because some of the lenses that were added displaced the image a bit, but the solution is accurate and everything is fine. Okay, so now we have now that I found this algorithm to solve this problem, now we have to implement it in a robust way. And this is more tricky because in the end, I checked that going to second order is not really convenient because it converges in a few steps, but the overall number of operations is the same. And also dividing by poles is not convenient because it introduces discontinuities in the phase because we are in a complex space. So it's not really nice. So my current implementation is to use the simplest algorithm, so first order Newton's method on the lens equation, and start from a list of educated initial guesses. So for each image, I can I have an idea of where to find the image. For example, for the primary image, I can start from the source position plus small displacement due to the other sources, and this will converge somehow and on the primary image of one of the positive parity images. For negative parity images, we can do the same. For example, this is good for far lenses. This is good for the lenses in regions where the shear is greater than 1. So you have the two possibilities for the negative parity images. And for additional images, we know that they come all around the critical curves. So we just have to, for example, to use a loosely spaced grid around each mass, for example. This works quite fine. But then I want to stress that this is work in progress. So any ideas to make it work perfectly are welcome. Maybe in the hack section where we can have a group thinking about it. So, but it's really, I really want to stress that we have the possibility to have the solution to the lens equation for any number of lenses. We just have to have it robust and in order to find all possible images. And so then in the end, you can have some fun with many lenses and take a source on the in points where you have self-intersections of the caustics and see whether you can recover the images. So it starts to work fine, but of course we need a lot of testing. So it's something I'm developing right now, actually. Okay, so well, these are the conclusions. Well, just also the time is over, so you can see that we really have the key to overcome this problem of the multiple lens equation and go to an arbitrary number of lenses. We just have to fine tune the details and find a robust way to find all images. Okay, that's all.
Thank you. We have time for one or two questions. Maybe Matthew, can you start?
This is a little bit off topic. So for the caustics of multiple lenses, you have different segments of the roots, right? You have different roots that correspond to different segments of the caustic. Can you identify which lens they are associated with? That might be helpful for classifying.
You mean associate images to lenses?
Caustic segments.
Caustics. Oh, you mean in this image? So Well, for example, this critical curve is associated with this cost. Okay, okay. This, of course, you can make a match between all of them. But of course, you have these big critical curves with all perturbations due to many planets, and then you can see here how the corresponding cost looks like. So in that case, it's everything is merged all together. But in principle, yes, you can say, okay, for example, I see that this region corresponds to this region. So you can of course this is useful, for example, to have some guiding in order to say, okay, if I'm here with my source, I'm here, I can expect an additional image coming here. Okay, yeah, so this is useful, definitely.
And I think we don't have time for future questions. Sorry for that. Yeah, you talked longer. Sorry.
Okay.
Let's thank Valeria once more. And Fran Bartolic from St. Andrews is our next speaker.
Hi. Okay, so I'm a second-year PhD student working with Martin Dominic at the University of St. Andrews. So a lot of what I want to say for today has been said already by Eric and Dan, so hopefully I have less work to do. So most of the talk is really kind of talking about the kinds of assumptions we make in Bayesian models of microlensing events and how those assumptions affect the results that you might care about. Okay, so let's start with the basics. Okay, so here's some data. This is microlensing event, and we can decompose it roughly in two parts. One part is the forward model, and the other part is the noise model. And the forward model in this case is, for example, your VBB binary lensing. And there's a lot of freedom in this forward model. You can have single lenses, you can have multiple lenses, you can have finite sources, you can have parallax, and so on. There's also a lot of freedom in the noise model. A lot of work has been done on the forward model in the past few decades, not as much on the noise model. So in most of this talk, I'll focus on the noise model. So let's take, for example, the simplest microlensing model, which is the point source, point lens model, and see how these look like, okay? So for point source, point lens event, model, you only have 5 parameters. You have your 3 Pyczynski parameters, which are nonlinear, and you have your 2 linear parameters, which are the fluxes, the source flux, and the blend flux, FB. And the magnification is given by these terms as well here. And the mu here stands for a mean that enters into Gaussian distribution. It doesn't stand for a magnification or anything like that. So the noise model is called the likelihood function, and it is the probability for the data, so the observed fluxes, given the model parameters, theta. And the simplest thing that we assume in microlensing is that the noise model is simple Gaussian white noise, which means that it can it's just a product of Gaussians going from 1 to n, when n is the number of data points. And so this likelihood thing, if you take the log of this thing, you get your chi-squared up to a minus sign and a constant, okay? And a likelihood is a generative model for the data, which means that if you give me some fixed set of parameters, using this thing, I ought to be able to generate something which looks like real data. Okay, so before I talk about how to extend this thing further, I just have a short aside on the simple point source point lens model. So if you take this as is and use some simple set of priors and you go and sample the posteriors for all the parameters, what you find is you have very strong correlations between some of the parameters, in particular these flux parameters and also U0 and TE. So these are the posterior samples. And what this tells you is that maybe you should reparameterize your model. And we've heard from Eric how important reparameterization can be. So there is an alternative set of parameters you can use, which is due to Martin Dominic. It's this set of parameters here. So it's delta F and the F base, which are new flux parameters. And the model is again linear in these new parameters. And basically, the delta F is just the difference between the peak here and the baseline, and F base is just the baseline. And these new parameters map to observable features much better. And if you sample in this new space, you get much nicer posteriors. Okay, so yeah, I would recommend this parameterization, and you get orders of magnitude improvements in sampling as well. So going back to the noise model now, so here we have again our likelihood function, or the chi-squared, and we can rewrite it in a slightly different way using matrix notation. So here is exactly the same thing, but now we have this covariance matrix sigma, and you can also write it using this notation, and it's, again, the same thing. So this means that the fluxes are sampled from a multivariate normal distribution with some mean mu and some covariance matrix sigma. And what we generally assume is uncorrelated noise, which is, in other words, the covariance matrix is diagonal, and there are no off-diagonal terms. Okay, so that's almost certainly wrong, right? That's probably not a good assumption. So how can we generate some off-diagonal terms? So we can't just specify n squared minus n numbers. We need some way of modeling those off-diagonal terms. And Gaussian processes are precisely the framework for doing that. So what are Gaussian processes? So formally, Gaussian processes are probability distributions over functions. So if you have just a regular probability distribution, if you take a sample, you get a number. If you take a sample from a Gaussian process, instead of a number, you get a whole function out, okay? And this function is defined by something that's called a mean function and the covariance function. In practice, what it boils down to, if you have just a discrete set of points, such as time measurements, the Gaussian process is just a sample from a multivariate normal distribution with some mean mu and some covariance matrix sigma. And the mean mu is really not important. The key point is this covariance matrix and how you define it. And the way you define the covariance matrix is by using this covariance function, also known as the kernel function. Okay, so the key point is this kernel function. So here's an example of one sample from a Gaussian process with a specific kernel function. So this is a very, very famous kernel function, very popular, probably overused. So it depends on your inputs, okay, evaluated at 2 different points. It has this form, and it has 2 parameters, which are often called hyperparameters. So there's a length scale L, and there's this lambda, which gives you like the scale in the y direction. And basically, the way you, so these are, so each color is a different sample from this GP, Gaussian process. And the way I plot this is simply by drawing samples from a multivariate Gaussian with a covariance function specified by this, and a zero mean, okay? And the functions look like this. There are many other choices that you can make for kernel functions. Another example is, for example, the maternity 3/2 kernel, and you can see the functions are a bit rougher. The previous kernel gives you infinitely differentiable functions. This kernel gives you twice differentiable functions. You can do many different things with kernels. You can sum them, you can take a product, you can compose them in functions, and so on. Okay, so how does this relate to then to our likelihood? So I told you just the GP is just basically a multivariate Gaussian. Our likelihood is as well a multivariate Gaussian, right? So same thing we had before, but now we don't assume that the noise is, that the covariance matrix is diagonal, but rather we add this additional covariance matrix, which is generated by this kernel function. And the kernel function depends on only the time, okay? So it depends only on the difference. Say I have like 2 time measurements, T1 and T2, so the kernel function depends only on the difference between the 2. Okay, so one problem with this, so here we have our likelihood function, we have a kernel, we can decide on the kernel. The problem with this is, say we have like 2,000 data points, we have to do a matrix inverse here. That's very expensive. It scales as the cube of the data points. That's very bad news. We don't have enough memory to do that generally. Fortunately, thanks to Dan Foreman's Mackey's Celerité code, you can do GPs in linear time for a specific set of kernel functions, which are still very flexible. And that's what I do. And you can do 2 things. You can either optimize the likelihood function, or you can sample the posterior probability distribution. So I'm a Bayesian, I like to sample. So to sample, I need to specify a set of priors as well as the likelihood function. And the only note I have here, we've heard from Nathan before, no such thing as uninformative priors. But also I would add that if you dealing with GPs, you have to think about your priors for the hyperparameters And in particular, for this length scale parameter, you want to avoid overfitting. And one prior which works quite well is the inverse gamma prior, which puts doesn't put a lot of probability mass below, say, the median spacing of the data points, because your data can't really inform the model about those scales. Okay, so we use Bayes' theorem. We sample the posterior. Other people have talked about Hamiltonian Monte Carlo. I use Hamiltonian Monte Carlo for the reasons they've mentioned. And what you get, so you get a fit which looks like this, for example. So this is just like a toy example. And does it matter? Well, yeah, sometimes it matters. It depends on the data. So for example, in this case, the posteriors that you get for the Einstein crossing time can be quite different if you assume white noise versus if you assume some sort of GP model for the correlated noise. And it depends on the data. So for some data, if the data is perfect, then it doesn't matter. If you care deeply about, say, low mass planets and the number of data points is very small and the signal to noise is very small, then it matters a lot more. Okay. I'm running out of time, so I'll skip this and just leave you with the take-home messages and some ideas for the hack session, if you're interested. Thanks.
We have more time for questions this time. Nobody? Oh, sorry. Yes, go ahead.
From the few I knew about Gaussian process, and I read on various documentation, I read that Gaussian process could have a tendency to overfit your data. So can you have some word about it?
Yeah, so that's what I mentioned about the prior. So if you just use a uniform prior on, say, this length scale parameter, so you could push those functions to be basically, to be affected by every single data point, and you want to avoid that. So this inverse gamma prior is something that I think Andrew Gelman suggested, like the STAN team. So that avoids kind of pushing the length scales to too short values. So the length scale in this case is a time scale because we're dealing with time series data.
Valerio?
Coming to one of your last few slides, you said that depending on the model you inject for the Gaussian prior, your posterior probability for your physical parameters may change.
Yeah.
Okay. But this is quite concerning because in the end we are modeling our noise with this Gaussian process. We are modeling something that is completely out of control, because if we knew the origin of this correlation, you could correct for it. For example, if we have a correlation with seeing in the photometry, we can track it and correct it, and that's a possible approach. But if we are completely ignorant about the source of systematics, this means that in practice, we have, depending on the model we use, we get a different result. So in practice, if you don't want to be conservative and say, I don't know what is the source of systematics, then probably the possible way to deal with this is just to increase the error bars and get a larger error bars on the physical parameters. So probably this, in the end, this is equivalent.
Maybe Eric Ford wants to comment on that, no?
Yeah, so I don't think increasing the error bars does the same thing, because I simultaneously increase the error bars here. So I treat also the error bars as a free parameter, the rescaling factor, and you still see the difference between the GP and non-GP. So your point about not knowing the source of the systematic is exactly my motivation for using GPs, because you don't assume a specific parametric form such as polynomials, okay? You assume a broad class of functions and properties like differentiability, okay, or yeah. So the assumptions are less severe in this case, I think. And it's probably better than doing nothing.
Last question from Peter.
So you should have a fit of a particular Microlensing event. How long did that fit take?
So without the GP, it takes like less than a minute for thousands of effective samples. With Hamiltonian Monte Carlo, with the GP, it takes a few minutes. Yeah.
Okay, let's thank Fran once more. Yes, and Yuki Hirao is our next speaker.
Hi, my name is Yukiro. I'm a PhD student at Osaka University and working with Dave at Kodatsu. Today, I'm going to talk about more data release and the analysis of binary and planetary events from more 9-year analysis. So MOA has conducted a high cadence survey observations towards the galactic bulge since 2006 using MOA-2 telescope at Mount John in New Zealand. And MOA will release its retrospective microlensing light curve data from 2006 to 2014 as a part of Japanese contribution to NASA's WFIRST project. Release date has not been determined, but it will be after the agreement between NASA and JAXA is signed. And the images have been reanalyzed using different cut and criteria from MOA alert system. So we found lots of events which were not alerted by the MOA alert system. So this figure shows the observation field of MOA towards the galactic bulge. So we use the MOA-CAM3 wide field of camera on the right, and which consists of 10 CCD chips. And this green box shows the area that can be covered by one observation. And there are 22 observation fields, and they cover about 50 square degrees in total. From 2006 to 2008, GB5 and 9 in red circles were observed once per 10 minutes, and other fields were observed once per 60 minutes. But after the 2009, we changed we optimized the observation strategy, and these 6 fields in red circles were observed once per 15 minutes, and these 6 fields in orange boxes were observed once per 47 minutes, and other fields were observed once per 90 minutes, except for this GB6 and GB22, which were observed once per night. And the total number of images of each field from 3,000 to about 30,000, depending on the observation cadence. And here is the number of events. Through the offline analysis, we have detected 22,862 variable events. And we fit all events by single lens, and we check the light curves by eyes and classify the event if they are the microlensing or not. And we found that 6,177 microlensing event candidate, which includes the 5,109 single lens candidate, and 124 short single lens candidate, and 576 binary lens candidate. And the other events were classified as moving, novi, CV, and so on. And for the data release, only the light curve on microlens candidate will be released. And there are more than 2,000 microlensing event candidates which were not alerted by MOA alert systems. So data format has not been decided yet, but it will include time in HAD, flux, and its error, and sync, and air mass, and so on. And also the coordinate of the event. I'd like to mention that the sample includes 26 planetary events, which were used by a statistical study by Suzuki et al. 2016, such as this MOA 2009, Barge 319, and MOA 2009, Barge 389 on the right. So after the data release, you can play around with this data. So I will show you some example of binary events. These are the events which were not alerted neither by Moore or Ogle. These are Moore being 69 and Moore being 149 and Moore being 44 and Moore being 32. These Moore being numbers were temporarily assigned when the event was identified as binary length candidate. And we have found several short duration binary such as Moore being 44 and Moore being 32. And these are the examples of events which were alerted by Ogle. And as you can see, more data covers some anomaly features such as caustic entry and caustic exit of this event. So with Ogle data, these data is help us to constrain the microlens parameters. So we now have a lot of binary candidates. We conducted systematic modeling for all alerted binary length events. So the motivation of this is to find the planetary candidates that was previously missed, and to get the microlens parameters and generate solutions, especially for the mass ratio Q for the statistical studies. And so we will measure the mass ratio functions for all mass ratios from planets to stellar binaries with detection efficiencies for binary length event, like Yoshi did in his 2016 papers. So for the statistical study, we need an automated way to select the binary events. But for the as a first step, we picked up the anomalous event from which were not alerted by eyes. So and we found the 242 events from out of 2,402 events. And we conducted the standard binary length fit, and so as not to miss the global grid search, so as not to miss the local minima, we conducted the global grid search by fixing the mass ratio, separation, and angles. And we used the MCMC and image-centered ray shooting method. Here is the first planetary candidate from our 9-year analysis, Ogle 2006, Valis 332, or Moore being 17. So this event was already alerted by Moore, Ogle. But with more data, we found that the best fit model has the planetary mass ratio. So my next speaker, Clement Rank, will talk about this detailed analysis. So we will go to the next event. So this is the second planetary candidate, Morbin 29, that Iona Kondo presented her analysis yesterday. So this event was not alerted neither by Moore or Ogle, but they were on the footprint of their observation field, and the anomaly was covered by thanks to the high cadence observations by Moore. And she found that the best fit model has a planetary mass ratio of 1.6 10 to minus 2, and the system consists of a gas giant planet around brown dwarfs. This is the third planetary candidate, Ogle 2014, Valis 1367, or Moore being 116. So this event was also alerted by Ogle, but with more data, we could also get the planetary mass, the best fit model with planetary mass ratio of 1.8 times 10 to minus 2. And this event has close-wise degeneracies, and further investigate is needed, but we didn't measure the clear finite source effect, but there is a good chance to get the parallax effect because this the time scale of this event is very long. And the Bayesian analysis indicates that this planet is a very massive planet, around 12 Jupiter mass planet. So we also found some events which are the planetary and binary degenerate solutions. This Moabin 41 is one of such events. At first, we found the best fit model, which has the planetary mass ratio of 1.8 times 10 to minus 3 for this event. And this is the acoustic geometry. But Dave also modeled this event, and he found that this short duration stellar binary can explain this event better. And so, and this is acoustic geometry. So our search method sometimes miss this kind of short duration binary. So we need to pay more attention for those events.
Did you check if there's Ogle data for these, even when it's no Ogle alert?
For this event,
Yeah.
I think there is no Ogle event.
No, Ogle data.
Ogle data? You mean?
Right. Is this event in the Ogle field?
I don't think so.
I think we checked for this one. I'm not absolutely certain. We checked for a number of them.
Yeah. So here is a summary on future work. So more we released data from 2006 to 2014, and we conducted a systematic model of all binary events which were not alerted by more alert system. And we found 3 planetary candidates and several events which have degenerate solutions. For the future work, we conduct this systematic modeling of all binary events, and we need to address the issue of degenerate solutions. And we measure the mass ratio function for all mass ratios from planets to stellar binary with the detection efficiency. Thank you.
Markus?
Very much for the nice talk. Could you please quickly comment on the data reduction and how you've recovered the events and why they weren't in there in first place?
Sorry.
So could you comment please on the data reduction and how you recovered these events?
So I think Taka-san, Smith talk about this.
I used a different method from Ian. That's it. And sometimes Ian mask around the barrier booster and the saturated pixel, and I used a different number of the pixel to mask or that kind of things.
Well, most of the events are 2006.
Right, and 2006, that was at the beginning of the Ian's alert system, and he only found about over the hundreds of events. So that's just during the preparation period. That's one of the main reasons.
Yossi, yes, you have a question?
Clarifying question, maybe Taka answer it. So the main difference is in the data reduction, not in the search algorithm. So it's the same search algorithm as the earlier warning system, like same thresholds or
similar, but the detail parameterization is different.
So is there a prospect to adjust what you learned to the earlier warning system to find these in real time in the future? Okay, and the second question, are you sure that all of these are, the very short anomalies are all microlensing events? Some of them look like just a spike with no wings of an event.
Yeah, I checked the baseline, whether there is any other flaring episode or not. But not 100% sure, but we checked.
Jan?
You haven't mentioned how much of those 6,000 new events were also found in early warning system before. Did you check for that?
Sorry, I didn't count, but yeah, there are a lot of events which were already alerted by Ogle in 2000, 6,000 events. Yeah.
Rachel?
So given that you are releasing just the microlensing events that you've detected rather than the complete data set, have you considered conducting an analysis for systematic noise across the whole data set?
I'm not sure for that. Maybe he can.
we suppose most of the systematics are removed.
So you use some detrending algorithm?
Yeah, which they implemented.
Okay, I don't believe that was described in the talk. Could you tell us more about it?
I mean, I think it's described in my 2012 paper on short binary events from the 2006-2007 analysis. The primary problem is differential refraction and movement of nearby stars, depending on nearby stars of different colors. And that's a problem in particular because it can give, both sort of daily correlations and yearly correlations.
Do you conduct this a systematics analysis for all of the events that you detect, especially some of the more subtle anomalous features?
Yeah, I did for all of them, all right colors.
Okay, let's wrap up the discussion and thank you once more. And Ingushin, is our next speaker.
Yeah, thank you.
Can you please use the side screens for now? We're working on the center one.
Can you hear me? Oh, no. Yeah, it's on. Yeah. Okay. I'm Ingushin from Center for Astrophysics. I'm working with Jennifer Yi. So today, I will present the two microlensing planet candidate. Important thing is candidate, discovered by the KMTNet survey. I said these are candidate because I found a degeneracy between binary lens and binary source. So this is answer for the Dominic's question. So actually, I should introduce about the binary source and binary lens degeneracy, but already in the previous talk, this already introduced, so I will skip down. I just emphasize only one point. If we found this degeneracy, we cannot claim the planning. This is important key point. This is obvious point also. So I will present for first planning candidate. This event is KMT 2017, 1119. I found a binary lens solution for this event. The solution indicate that in the figure indicate that. Before that, I should explain this. For the binary lens solution, I found a close and wide. Okay, thank you. I found the close and wide solutions. The delta chi difference is about 6. In the figure, blue indicate the closed solution, red indicate the wide solution. The mass ratio is about the point. I mentioned I note that closed solution is the best solution. The mass ratio is about the 0.06. This is not too low to claim the planet, but Einstein timescale of this event is about the 3.5 days. It's really short. So this is a planet candidate. But important thing is I also found binary source solution for this event. Delta chi-square is about the 20. I will detailedly show this delta chi-square later. But important thing is this binary source solution is the different to the typical Gaudi case. Gaudi already showed the binary source have the less extreme flux ratio, and the separation between the binary source is the less extreme. I will show you about that delta chi-square. Delta chi-square 20 is the kind of the marginal things. So somebody say I can resolve this, somebody I cannot resolve this, but my conclusion is that this delta chi-square comes from the feed of the systematic of data. As you can see, even the best of all models show some systematic trend in the residuals. This means improvement comes from the fitting of the systematics. So my conclusion is that I cannot resolve this binary source and binary range degeneracy by using the delta chi-square. Well, anyway, there still remain the degeneracy. I try to determine the property of this Plany candidate. So I use the Bayesian analysis, and Bayesian analysis tells me the primary is the Plany-like host. This is the 0.01 solar mass. It's the means about the 10 Jupiter mass. Secondary is the sub-Jupiter mass Plany is about the 0.6 Jupiter mass. So this system, very interesting. This system is maybe a free-floating system, something. But important thing is, once again, there are binary source and binary range degeneracy, so I cannot claim this interesting system. So now I would like to say about how resolve this degeneracy. So actually, Gaudi already mentioned several methods to resolve this degeneracy. I mean, I said degeneracy means the binary source and binary range. So first method is the detailed analysis of the light curve. But as shown in the previous slide, I cannot using the chi-square difference for the resolving this degeneracy. So I cannot apply this method. The second method is to use the color information of source. Actually, KMTNet project regularly take the V-band image, but for this event, actually for another event, the V-band data is, the quality of V-band data is very poor, so I cannot apply this method. So now I'm sorry. Now I suggest another method. From the modeling, I found source flux is very different for two solutions. For the binary range solution, source flux is about the 0.15. For the binary source solution, source flux is about the 0.23. This means if I have a chance to take a follow observation using the adaptive optics system in future, the source will be measured about the 20.1 if the system is really a free-floating planet. If the source magnitude measured brighter than the 19.6, it means this event caused by binary source. I will present another degenerative case. This event has more severe degeneracy. From the binary range solution, I found the close wide degeneracy. The delta chi-square is about only 0.3, and both solutions indicate mass ratio is about 0.01. This means this system is a planetary candidate. Also, I found binary source solution, but in this case, delta chi-square is only less than 1. Another important point, the binary source solution also have less extreme flux ratio and less extreme separation between the source. As you can see, for the all model, we cannot distinguish for all models. It means the delta chi-square less than 1. I also try to determine the property of the planetary candidate. So I found this system may caused by Jupiter-class planet and M-dwarf host. This is quite a typical microlensing planet. And I should check the possibility to resolve this degeneracy, but as you can see, I cannot apply all methods for this event, especially for future adaptive optics observation cannot help the resolving this degeneracy because I found the source flux of the two models are identical. So I will summary of my work. For the one event, for the both event, I found the degeneracy. So I just reported these events are candidate of planet. For the one event, I can resolve this in future. For the other event, I cannot. This is important. This is the main point of my work. For the binary source solution, I found this binary source solution is a bit different from the Gaudy's case. Actually, Radek already showed this. So, important point is that this degeneracy can be existed for a wider range of the planetary event and also for the less extreme binary source systems. Thus, conclusion is that the binary source and binary range degeneracy can be a bigger problem for the discovery of planets than previously we thought. So that's it. Thank you.
David?
So one thing that you might try with the first system that you presented is to actually improve the photometry. On the fourth planet found by microlensing, we spent a lot of time with two different photometry codes working on it, and we found systematic errors in both set of photometry by comparing them and varying the parameters of the photometry. So, you know, in situations like this where the systematic error is preventing you from making a decision, I think maybe that's a good thing to try.
Well, actually, I would like to note that these data are already reduced by PySys packages. So, well.
So just try a completely different photometry.
Yeah, maybe.
And also, there's parameters in the photometry, and you know, by comparing different reductions, we found how to fix systematic errors in both of them by adjusting the parameters.
Yeah, thank you.
Markus?
Can you disentangle the scenarios spectroscopically with an IFU and observe these targets again? Or are the parameters not?
Actually, according to Gaudy's work, Gaudy suggested a method to resolve this degeneracy, that is the spectroscopy. But for both events, I cannot remember the exact number, but important thing is the spectroscopy is very challenging for these two events.
More questions? We still have time. No more, then let's thank Ingu. Clement Rank is coming with his talk, which will be the last talk of the day for the conference.
Hello, can you hear me? Yeah. Yes, so I'm Clement Rank. I'm a postdoc at NASA Goddard Space Flight Center. I'm very happy to be here today. As most of you know, I arrived today. And I will speak about this first new planetary event found during the retrospective analysis done by Takasumi and Moa. This is this kind of good news we have when we look at past data. So this event has been observed in 2006 and was actually has been observed also in Ogle 3 field. Ogle did one observation per day approximately in this field, close to the galactic bulge. So here is the first look at the light curves. We have only no follow-up data, only MOA and Ogle data. The main reason why this, as Yuki explained, the main reason why this event was not alerted by MOA is because this is the beginning of MOA 2 service, so no baseline data, and the alert system, I think, started during the summer. If we look in little bit more detail to this part of the light curve, we start to see a sudden magnification, sudden increase in the brightness of the target. And if we zoom in again, we recognize something like very clear feature, which is characteristic of acoustic crossing. So yeah, you all know that. So I started to consider a static binary lens model with finite source effect because it seemed we had data during the acoustic exit. And I started by a broad exploration on the grids along the separation, mass ratio, and orientation of the trajectory, the source trajectory compared to the lens. And after I refined the modeling with Markov chain Monte Carlo algorithms. So the best fit model indicates that the mass ratio is 0.77 10 to the minus 2, which would be, oh, thank you. Thank you. Yeah, so which would be consistent with typically a super Jupiter, could be consistent with a super Jupiter planet. One important point here is that the MOA data actually constrain pretty well the acoustic exit, so we have good hope to have a measurement of the source size. And especially thanks to these 2 points separated by 53 minutes. So this, the difference between the main competing model is the main competing models are allowed mainly because of this gap during this caustic entry, and the model differs mainly by the time when the source crosses this the edge of the caustic here. So this increases a little bit the uncertainties on the geometrical parameters. So we could measure pretty accurately the source size, which is 510 to the minus 4. And if you have a look to the marginal distribution over all the parameters, so here is the final result. And I would like to have a deeper look to the separation between the planet and the host, which is very close to 1. So this is in a case where we cannot really have two clear different competing models with a close wide model that we seen previously. So the next step is the source characterization. So to do that, from the light curve modeling, we have access to the brightness of the source. Then the next step is finding the extinction. So to do that, I built the color magnitude diagram. This is in blue, the ogle CMD. The green shows the CMD from the stars in the bad windows, and obtained by HST. And finding the location of the red clump, we can infer the extinction in the field. And on the other hand, I built the empirical color-color relation between the R MOA, so the brightness in the MOA passband, and the brightness in the ogle passband, as a function of the color V minus I. And so putting everything together, I derived the brightness and the color of the source corrected from the extinction. So this is where the source falls in the CMD. It's pretty red, in fact. And so the uncertainties are also large. And if you look at the value of the corresponding value of the proper motion, it's more than 12 milliarc seconds per year plus minus 3, which is a lot. So I wanted to investigate it a little bit more. And what I did, I fixed the best model, and I I derived the source brightness and color with only baseline data and the caustic. And on the other hand, so when I do that, the source color is shifted toward like much closer to the main sequence. And doing exactly the same thing, but removing the caustic, the source color like go in the opposite direction. This might be, well, this is what could happen if during the caustic crossing only, for example, one component of a binary source maybe is crossing the caustic. So if we have like a binary source model with 2 stars with different color, something like that could happen. So basically right now I am running models of binary source, binary lens. For now I don't find a competing model, but still underway. Second next step is that this target has been observed as part of the KSMS proposal led by David Bennett. We have data, observation from Keck, 13 images in narrow camera, 10 images in wide camera. Jean-Philippe Beaulieu and I think Josh, I don't know where, oh yeah, worked on the calibration. And a very preliminary analysis seems to indicate that the target, which is here, is slightly elongated. So this is very preliminary. Next steps is to combine all together to have a consistent picture. So at the very beginning, and actually at the time I wrote the abstract, I had to deal with several competing models that I couldn't really distinguish. This was before I did the error rescaling and I did the broad exploration. So, and this is a typical situation that I had to deal with, and I was looking for a method that could give me the relative probability within the competing models. So it turns out that at the end of the story for that event, it seems like all the competing models are ruled out. But for the event OB1670 that I analyzed last year, I think that there is one, it's a good illustration of this kind of challenge we all face in microlensing. So here, so this is the event, the light curve. Here is the anomaly. And what I would like to point out is, so there is in that case the close and wide degeneracy that we have already seen several times, which correspond to these two caustic topology and source trajectory. But there is also this kind of degeneracy in terms of source size. And this corresponds to these two situations where the source is a little bit larger and the distance between the edge of the caustic is smaller, and the opposite, a smaller source and a larger distance between the edge of the caustic. And what is interesting here is that the volume of these two solutions is really different. And initially, I ran MCMC here, and there were no way to jump here. So the question is, how can we include all this solution in Bayesian analysis and properly sample this posterior? So here is, so why is that important? This is another event, MB15337, where the close wide degeneracy has a clear consequence on the projected separation we derive from the Bayesian analysis. This is the two modes of this posterior correspond to the close wide degeneracy. Here is, again, another example that I hope we will work together on during the Hack Week Hack session. The model was done by Dave Bennett, where you have 4 solutions at very different mass ratio and different separations. And the challenge is, how can I sample, draw the posterior directly, taking into account all the solutions? So here our very first idea. I have like many more, especially after Eric Ford talk. I don't know if he is here. Anyway, and we will speak more probably during the hack session. But there are many MCMC sampler. Which one is the best to deal with this solution? Imagine you have the best algorithm, machine learning algorithm. You have identified your solutions, and now you want to do the Bayesian analysis. So I cite on two examples. So the first one we already speak. I think Etienne spoke about the differential evolution. Oh, and Marcus, Markov chain. So I tested where the basic idea, if you don't know, is from a location you to choose build a proposal. You use so you run many chains in parallel, and you use two randomly chosen chains to build a new proposal. And when you do that, so this algorithm is not really designed to describe multimodal distribution, but it seems that it's enough as to really use the word that Eric Ford used yesterday. It's enough in that case where there is the close-wide degeneracy to jump for the chain to jump and to give the relative probability directly from the two solutions without doing a MCMC here, and then combine the two weighting by the delta K square, which assume that the volume are similar. Another algorithm that is really designed to assess the relative probability between modes, I didn't test it in microlensing yet, is the repelling attracting metropolis algorithm, where the broad idea is to do a force down-up motion in density, so disfavor jump followed by a favor jump, and we do not accept the next point until we don't find this, we don't have this scheme. So it works very well. For example, in the paper I read on time delay in strong lensing. This is what you see here, and the modes are very separate, like really separated. The question that is still we still need to understand is, does it work in high dimensional space? So I leave you with this question, and let's experiment during the hack session on this topic. I would like to work with you and hear your ideas. Thank you.
Andy?
Well, first, just a comment that the relative volume or the jumping back and forth tells you absolutely nothing about the relative weight of these solutions. I don't have time to tell you why now, but hopefully I can tell you why later. I guess I'm okay. And the other thing is that this event was alerted by the Ogle early warning system on June 26, 2006. Yeah. And it's clearly shown in the data because they took a bunch of data extra themselves.
Yeah.
And so it just seems to me that it's a routine thing. MOA should do what KMT always does. Is anybody alerts something interesting, we always try to find it in our data. So why wasn't that done?
So it's, I didn't get the last part you said. Like,
why did this take 12 years? It didn't have to be discovered in MOA data. It was already alerted as an
I understand.
Event in
I
2006.
get it. Yeah. Well, in 2006, I was not.
Okay, you weren't even born yet.
I was in maybe even not in high school. So
maybe Dave can answer that question.
Okay. Just a comment on what you said about the volume in the parameter space. So one question I have is when the volume is very different, and for example, in the part where the volume is the smallest, the chi-square is the best, and imagine just next to this solution, you have a very large volume, we'll say, but slightly worse delta chi-square, sorry. So in that case, it's if
anyway, nothing about that volume. It's all irrelevant.
Hello, Dave. To talk.
Well, so I mean, in 2006, you know, I was into more collaboration, but I wasn't terribly active. It was, you know, the first year of the MOA 2 survey, and well, yeah, I'm not sure exactly why this event wasn't searched, but we have limited manpower, and you know, I mean, well, you know, it's sort of hard to say.
But if you know compare this to you know something the same, you compare this to something the same year, which was OGO 2006 109. So they also issued early warning thing, and also took a couple of extra points and notified people, and people got on it right away. So.
Well, I mean, there wasn't any anomaly alert sent out by OGRL on this, was there?
Yes, on June 26, 2006, there's early warning system. They say we have the anomalous event is done, you know, the very night of the anomaly.
Okay, I think we can continue discussion offline. So let's thank Clement once more.